Okay, this is problem number 7. You're going to construct an open rectangular box from an 8 by 15 inch square of cardboard, rectangle of cardboard, by cutting congruent squares from the corners and folding up the sides. What are the dimensions of the box of largest volume? What is the volume? Okay, so I have here, this is our rectangle, and this dimension here is 8, this is 15. So what this problem is asking us to do is cut congruent squares from the 4 corners. So I'll cut a square here, I'll cut a square here, I'll cut a square here, and I'll cut a square here. And these are supposed to be congruent squares. So kind of work with me on that. So I cut those squares out. And then, if you kind of put in some dotted lines here, we would fold the cardboard up on that dotted line, and on that dotted line, and on that dotted line, and on that dotted line. And what we would end up with is an open rectangular box. So our box would look something roughly like this. And there is no top on it, but roughly some kind of a box like that. And we want to look at those dimensions, and then we want to figure out what are the dimensions of the box of largest volume. So again, as in any of these problems, we kind of zoom in and realize, okay, we want to maximize the volume. So here is our rectangular box. Let's get the volume. And to do that, we come back to our original picture, and we look at these squares that we cut out, and let's say the square is x by x. It's a square, so both sides are the same. So it was x on either side of that. So now when we look at the box we made, it was 8 top to bottom. So this inside dimension here would be 8, but you took off x on both ends. So now going up and down to the dotted lines, that's 8 minus 2x. Likewise, back and forth would be 15 minus 2x. If you want to label that in the box over here, this is our 15 minus 2x. This is our 8 minus 2x, going this way and then going this way. So what is the height of our box? Well, you folded these sides, this side, or this side, or this side, or this side. You folded those up, and the height, guys, is right there. The height of that box is x. So if you've got this picture in mind, this problem is not difficult to do. We know the volume of a box. It's length times width times height. So let's get the volume. Volume would be 8 minus 2x times 15 minus 2x times x. We will FOIL this out, do a little bit of algebra before we take a derivative. So if I FOIL this out, 8 times 15 gives me 120. I know I'll distribute the x. So I'll get 120x. When I do the outside, I get minus 16. The inside gives us minus 30. So minus 46x. Don't forget to distribute the x down here. So 46x squared. And last is 2x times 2x is 4x squared. Distributing the x is 4x cubed. You can check the algebra on that, but that should work out if you FOIL that out and then distribute the x. So this is our volume. We want to maximize the volume. You know how to maximize things with calculus. Take a derivative. So here's v. V prime becomes a derivative. It's 120. It becomes minus 92x plus 12x squared. And this is a little bit exciting because, look, it's a quadratic. We know for a derivative, to find maximum noise, we take the derivative. We know we want to set it equal to 0. We're also looking where the derivative is undefined, but it's a polynomial, so it's defined everywhere. So we're going to find out where this is 0. You might be thinking, let's factor that. And that 92 is a little bit troubling. 12 goes into 12x squared. It goes into 120. 12 does not go in nicely to 92. So if you're going to factor that out, it would not go in nicely to 92, so out of luck. So instead, you are probably reaching for your calculator, and so am I in this particular problem. Let's put it on the screen fully so we can see it here. And let's go to our polysmelt. That's always a nice way to solve these. See if we can find it somewhat quickly here. Thank goodness. And we'll get going on this problem. Press any key. And I want my root finder. And our degree of a polynomial, it's a second degree polynomial. And my leading coefficient is the 12 from the 12x squared, followed by a negative 92. And hopefully as I'm doing this, one thing you're thinking is, wait, we're going to get two answers on this problem. It's a quadratic. We're expecting two answers. How can there be two? Maybe your second thought is one is a max and one is a min. That might be your thought. But let's see what we get for these two answers. So 12, negative 92, 120. I'll come over here and solve it. And I get 1.66666, which looks like 1 2/3. And my other answer is 6. Let's just keep those so we can remember those. I think I can, but just in case, put our calculator. And let's see what we get with this. So our two critical points where x equals 1 2/3. We'll just pretend we did that by hand. And our second critical point is x equals 6. Now, we've got to come back to the problem. And I didn't at the beginning talk about the endpoints, but we should talk about the endpoints a little bit because it's going to affect our critical points. So we take a look here, and we're taking out this box, this x by x box in here. What's the least x could be? Well, it's got to be greater than or equal to 0. And what's the most x could be? Well, look at this side of 8. If you're cutting a box out of the bottom and out of the top, does it make sense that x no way could be bigger than 4? Because you cut 4 from the top and 4 from the bottom. There's nothing left here to fold up to make a side. So our x is actually bounded between 0 and 4. Our endpoints are 0 and 4. So this critical point of x equals 6 would not make any sense in our particular problem. It would have kind of a theoretical minimum for some kind of a volume of a box that we can't make, but in the conditions of our problem, 6 makes no sense. Okay, hopefully 1 2/3 will be a max, because if you think about our endpoints, if we cut out 0, that's flat, that doesn't have a volume. If you cut out 4, the same thing, you have no side over here, that's not going to give us a volume. So we're kind of betting on this 1 2/3. Let's take the second derivative, and I note here 120 goes away. I get a negative 92. I get a 24x. I'll check my second derivative at 1 2/3, otherwise known as 5/3. I'll get negative 92, and I'll take 24 times 5/3. Reduce it, I get an 8, and it looks like a negative 52. So by the second derivative test, my critical point, the second derivative is negative, so my graph is concave down at that point, and concave down means I have found the local max. It is the only critical point that we have, so our function goes from increasing to decreasing. Our derivative would change from positive to negative. By the second derivative test, we have found the local max. Now, let's answer the question. What are the dimensions of the box of largest volume? We found x, but let's find all the dimensions. And then what is the volume? All right, so x is 1 2/3 is our local max. Let's get the other dimensions. We had 1 2/3. Then we have 8 minus 2x. Minus 2 times 1 2/3. 2 times 1 2/3. What is that? 3 1/3. So 8 minus 3 1/3 is 4 2/3. And 15 minus 2x. And again, 2 times 1 2/3 is 3 1/3. So 15 minus that would be 11. 11 2/3. Interesting dimensions. So our dimensions are 1 2/3 by 4 2/3 by 11 2/3. And they'll seem like really strange numbers. Hopefully, if you're listening to this, you will check the answer key and make sure that's right. And if it's wrong, let me know. But those are the dimensions. And now, let's check what that volume would be. So let's pull out our calculator for that. Put out of here. And I've got 1 2/3, otherwise known as 5/3. I'll take it times 12 14/3. I'll take that times 33 35/3. Oops. 35/3. And this is our maximum volume for this box, 90.7407. We'll save that here. All right. It doesn't hurt to check this answer another way. And I could have done this right from the start. I've got my calculator. Let's just take our volume equation and graph it and check that max. So our volume was 8 minus 2x, and that way I'll find a mistake if I've made it. 8 minus 2x, 15 minus 2x. And again, what am I using here? I'm using this equation right there. That equation was our volume equation. Bring back the calculator. 8 minus 2x, 15 minus 2x times x. When I set up my window, I think about this. This is x. We said x, it can't be less than 0. And it really can't be more than 4. Oops, skipped one there. Can't be more than 4. Our scale will count by ones. Y's, well, you're not going to have a negative volume, so 0. It looks like the max we said is 90.7. Let's just go up to 100 in case we didn't get that right. And our scale here is 10. And we hit graph. And we get a nice volume graph like that. And again, we can kind of see that maximum in here. And maybe we'll trace on it. I'll just try this 5/3. Doesn't prove it. Oops. Try that again. So try 5/3. Take that out. Hit enter. 90.7. That's what we had for our volume. Come a little to the right. Ooh, did that get bigger or smaller? 708. I got a little smaller. Come a little bit to the left. It's getting smaller. That certainly does appear that we have found our max. It certainly that part was right. I was just questioning the dimensions a little bit. Those seem a little strange, but I'm a lot more confident with those as well. So that completes problem number 7.